All right, so good afternoon, everyone. Let's start. Welcome back to our class. Okay, and today we'll be studying about heat engines. Okay, so this is the application of our lesson for last week, which is all about the second law of thermodynamics. Okay, so let us have this one. For today, we'll be learning about this one. We have two objectives. Number one is you should be able to state the implications of thermodynamics in heat engine. And number two, explain and illustrate how a heat engine works. Okay, so we hope to be able to do that after the lesson, right? But before we proceed with the heat engine, let us have a review first. Okay, so let's see if you can still remember. As I have said, for the past weeks, we have been discussing about the laws of thermodynamics. Okay, now can you remember what does the first law of thermodynamic tells us? What is the first law of thermodynamic all about? Who can still remember? What is the law, the first law of thermodynamic all about? Anyone? First law of dynamics. No one? Already forgot na, huh? Okay. So the first law of thermodynamic tells us that energy is conserved. Because the first law of thermodynamic is all about the law of conservation of what? What is this about law of conservation of what? Bloom. Is Bloom here na? The first law of conservation of...
Energy.
Okay, that is correct. Thank you. Okay, so the first law of thermodynamic tells us about the law of conservation of energy, right? So because in here, energy is conserved. Okay, but unlike any other conservation of energy, the first law of thermodynamic follows the law of conservation of energy, taking into consideration the internal energy of the system, right? Internal energy. When we say internal energy, this is all about the energy inside the system, right? And then last time, we have learned that there are three types of kinetic energy. Do you still remember three types of kinetic energy when we discuss about the first law of thermodynamics? Prim? Can you still remember, Prim? How about Bio, number 13? Do you still remember the three types of kinetic energy which constitute the internal energy? I'll give you one. We have translational kinetic energy. Can you give the other two? Translational kinetic energy. Can you give the other two types of kinetic energy which constitute the internal energy of a system? Hello, Pio? Can you remember? Translational kinetic energy. Okay. How about if the atom is rotating? What kind of kinetic energy does that atom has? If the atom is rotating, what kind of kinetic energy will that atom produce? Prim. Hello, Prim. Do you have a student here? Do you have students here? Prim. Hello,
When I
Prim.
forgot that. Yes.
Okay. If an
Yeah.
atom is rotating, okay, what kind of kinetic energy does that atom has? I have. Prim, if an
Atom hả?
yes, if an atom or a gas, if the atom of a gas is rotating, okay, rotate. What kind of kinetic energy does that atom of that gas have?
Teacher, did you call me?
Yes. Can you help
I
Prim?
went to toilet.
Okay. Bill, all right. Okay. Prim first, Prim. If the atom of a gas is rotating, rotate, okay, it's called
rotation.
okay, that is correct. Rotational kinetic energy. Okay, rotational kinetic energy. Thank you so much, Prim. Okay, what about the other one? Last one. We have number one, translational kinetic energy. Number two, rotational kinetic energy. All right. How about the last one? Who can still remember? What if the atom of a gas is vibrating? Okay, vibrating back and forth. Okay, what kind of kinetic energy does that atom possess?
Vibrational.
All right, so that is correct, vibrational. Okay, so this three kind, don't forget na class, okay, these three kinds of kinetic energy constitute the internal energy of a gas. Okay, again, number one, translational. Translational is the ordinary kinetic energy of motion. Okay, number two is rotational, when the atom is rotating. Number three is vibrational, when the atom is vibrating. All right. Okay, so that constitute the internal energy of the gas or of the system. Right. Next, next one here, for the first law of thermodynamic, we have this equation form. Do you still remember equation form? Okay, this one is delta U, or change in internal energy, equals Q, which is heat, plus W, which is the work. Okay, now can you tell me this one in sentence form? Do you still remember how do we say this in sentence form? Uh, delta U, which is the internal energy or the change in internal energy, equals Q, which is the heat, plus W, which is the work. Anyone? Is it hard? How do we say that in a sentence? We can say that in a sentence like, the change in internal energy of a system is equal to the amount of heat added to the system plus the work done on the system. Okay, the work done on the system. Okay, again, the change in the internal energy of a system is equal to the amount of heat plus, okay, plus the amount of work done on the system, right? That is the first law of thermodynamic. I hope you do not forget that. Again, first law of thermodynamic is about the law of conservation of energy, right? Energy. Okay. What about the second law of thermodynamic? What do you remember about the second law of thermodynamic? Okay, can you give me at least one word that you remember, a very important or significant word that you remember about the second law of thermodynamic? How about entropy? Do you remember entropy? ENTROPY. Do you still remember that for the second law of thermodynamic? Entropy. What is entropy? Who can still remember entropy for the second law of thermodynamic? No one already forgot?
Like disorder.
Okay, it's the disorder of a system. That is correct. Okay, so entropy is the measure of the disorder in a system. All right, so the second law of thermodynamics tells us that the amount of entropy never decreases. Okay, it never decreases. It always increases. Okay, it always increases. Like if we have a closed system like this one on the slides, the yellow one here says the entropy never decreases. It always increases. Okay, as time passes by, entropy becomes higher. Okay, the entropy becomes higher. It means that um, the extent of disorder is becoming more higher. Okay, that is what the second law of thermodynamics tell us, right? So for today, we're going to study about the applications of that. Okay, application of at least we're going to focus on the second law of thermodynamics, and this is all about heat engine. Okay, so what is a heat engine, teacher? Okay, now when we say heat engine, I'd like because these two students are always present. Top, hello, top number two. Top. Top absent. Okay, if top will not answer, I will mark top absent because it means top only checked the attendance and then left the class. Is that correct? Top not here. How about another one? Okay, top is not here. Next, Kla, number three. Kla, are you here? Kla.
ครับ teacher
Okay, Kla, can you read this one? What is a heat engine?
heat engine is a device ใช่ไหม teacher
Device
device used for converting heat energy to mechanical work.
All right, thank you so much, Tongkla. At least Tongkla is still present. Thank you. Okay, so heat engine. Okay, we have here an example of a heat engine, a simple heat engine. This is a device used to convert. Okay, it is converting heat. Okay, heat energy to mechanical work or mechanical energy. Okay, from heat to rotation or mechanical work. Okay, so that is the function, basically the main function of a heat engine, to convert heat energy to mechanical energy. But the main question is, how does a heat engine work? All right, how does a heat engine work? Now, there are three important parts of a heat engine. Okay, so based on this illustration, there are three important parts of a heat engine. I hope you list this down so that when I ask you again next time, you can answer me. Okay, so the first part is there should be a source or hot body. Okay, there should be a source. Okay, number two, another one is there should be a working substance. Okay, working substance. And number three, there should be a sink or the cold body. Okay, again, these are the three important parts of a heat engine: the source or the hot body. Number two, the working substance. Okay, the working substance here could be a gas or a liquid that turns into gas. Okay, meaning, where's that? Let's go back. Something in here, it could be a gas or something like a liquid that turns into gas. Okay, that's one, two, three. Okay, source, again, source or the hot body. Number two is the working substance, and number three, the sink or the cold body. Okay, now in here, let me press the next. Okay, in here, just the same in here, the working substance, the circle one here, is taking a long cycle of operation. Okay, it's taking a long cycle of operation, and in this process, the working substance absorbs heat. Okay, it is absorbing here. The working substance here is absorbing the heat from um, the hot source. Okay, it's absorbing the heat from the hot source and then transform part of it into mechanical work. It's transforming part of the heat, or yes, the heat into mechanical work, and the remaining part of the heat is reject into the cold sink, right? It's reject into the cold sink. And then after the operation, the working substance comes back to its original state, right? That is how this is being done. Let me repeat again. The working substance absorbs heat from the hot source or from the hot body and then transform some of the heat into mechanical work, and then some of the heat is reject into the sink or the cold body, right? Now in here, heat is never converted to mechanical energy, right? Heat is never completely converted to mechanical energy. Why do you think? Heat is never completely converted to mechanical energy. Do you agree with this? Heat is never completely converted, right? This is it means that the efficiency of a heat engine is never equal to 100%. Is that correct? Do you agree with that? The efficiency, meaning there is no machine that is 100% efficient, right? Meaning that the work output, okay, is always less than, okay, the input, okay, because some of the energy is wasted as heat. All right, and we measure that. We have what we call efficiency of an engine. Okay, how do we do that? This is the ratio of the external work done to the amount of heat absorbed from the source, right? So in other words, here the mechanical work is not always 100%. Okay, if the heat here is 100%, it's not always 100% that will be passed through here, okay? Because some of this will be transferred to the sink, okay? Will be rejected to the sink. So it's not always 100% efficient, okay? That's the principle about heat engine, right? Let me proceed to the next slide. Okay, so this one here, heat is never completely converted to mechanical energy. Let's say if you had 100% here, so the output is not always 100%, right? It's not always 100% because on the process, heat is released here, right? Heat is released to the engine itself, right? That's why it's not always 100% efficient. All right. Now, by this, it means that we have at least two consequences of the second law of thermodynamics. Okay. Let us this first one. Let me call at least participate by reading. Where is pair number 16? Hello, pair. Number 16. Can you read the first one, please, for me? Pair. Okay, pair is not here. Nowhere. Number 19. Nowhere. Hello, nowhere.
Yes.
Okay, can you read the first one, please?
There is a theoretical limit to the efficiency of a heat engine.
All right, so that is correct. Pair, there is a limit to the efficiency of a heat engine. Okay, in other words, the efficiency is not always 100%. Okay, the output is not always 100%. And number 2, where is Mudtanoy number 22, please? Mudtanoy, can you read number 2 for me?
Yeah, teacher. His will never spontaneously, teacher.
Spontaneously.
Spontaneously move from cold place to warm place. Works is required to pump heat, teacher.
Okay.
From cold place to warm place.
All right, thank you so much, Mutanoy. Okay, heat will never spontaneously move. Okay, meaning when I say it will never spontaneously move, it will not move by itself. Okay, it will not move by itself. Like if I have a coffee in here and I pour some coffee inside, the coffee will not just move out of the cup by itself. Okay, that is what we mean by that. Heat also will never spontaneously move from cold places to warm places. Okay, to do that, work is required. Okay, work is required to pump heat from cold places to warm places. All right, how do we do that, teacher? Okay, let's say I have here an illustration. Okay, let's say here, imagine we have two rooms. Okay, room number one and then room number two are both hot. Okay, hot, they are both hot. Okay, let's say I want to make room number two hotter and room number one cold. Okay, it means that I'm going to pump the heat, okay, out of room number one and bring it to room number two. Can we do that? Okay, is it possible? Okay, pump uh, pump the heat from room number one to make it cold and room number two really hotter. Okay, really hot. Okay, is it possible? According to the second law of thermodynamics, yes, it is possible, but okay, what is the but here? Okay, what's the answer? What is the big no? If, but work is required, right? Work is required. Okay, so the second law of thermodynamics says that work is required. We need to do work. Okay, we need to do work. Okay, let's do this. Okay, let's say this is a video. I think let's see if we can play this one. Okay, so if we are willing to put work, it is possible. Okay, meaning we can make the room cold and the room number two hotter. Okay, so how could we create something to actually pump heat from room number one to room number two? How do we do that? Is it playing? Okay. All right, so what we're going to do is just, we are going to use this principle of compressing and decompressing of gases. Okay, we're going to compress. When we say compress, we'll just press this down. Okay, okay, so this one is compress. Okay, compress, meaning we're going to apply work going down here to compress the gas. Okay, and then in here, when we compressed, heat is released into the environment, right? Heat is released into the environment. Okay, what if we do the opposite? Okay, this one is compress. What if we decompress? Okay, okay, that is decompressed. What happened? What happened is the opposite. Okay, it will allow the heat to escape and it will become the gas will expand, up, okay, and then it will cool down. Okay, so meaning we can use this principle of compressing and decompressing of gas, okay, to make one room or one place to pump out the heat from one room to another room. Now, this is also the principle we're going to use to build our refrigeration device. Okay, the refrigerator, this is how the refrigerator works. Okay, in here, we have two rooms. Let's see. Sorry about that. Let me just continue. This is a video. Okay, and this one is long. Compressing, and heat is released in the environment. Decompressing, and become cool gas. Okay, so we're going to use this principle. Okay, let's say we have here two rooms. Okay, and inside this piston is a refrigerant. Okay, and here we have two rooms and a container filled with refrigerant. Okay, this is how it works. Okay, heat Okay, so we're going to compress it here, meaning it makes the environment heat, and then bring this piston on the other room to make it cooled, all right, to make it cold, and then bring it to another room. Okay, if we're going to do this process, so on and so forth, okay, if we're going to repeat this process again and again, in other words, we can make the first room number one, really cold, and room number two really hot. All right, because we are by just compressing and decompressing the gases inside this two place, room one and room number two. Okay, so meaning it is possible, okay, it is possible to make one place colder and pump the heat from that room going to another place and making the other place hotter. All right, just like this one. Okay, question. What are the three essential or important components, okay, that we have here in order for us to pump heat from room 1 to room 2? Okay, and on the previous slide that I have shown you, what are the three important components? Anyone? What are the three important components? Ploy number 1, 24. What are the three important components? First, what did we use to pump the heat from room number 1 to room number 2?
Teacher,
Yes.
I can see your screen.
You cannot?
Yes, at the first time.
Including the
Maybe
slide?
if I have problem with my internet, I can see your screen.
Okay, all right. Okay. Okay. Next, how about Bill? Hello, Bill. Can you see the slide, Bill? Bill?
Hello.
Okay, Bill. What are the three important components, okay, that we did on the first slide? Previous slide, I mean. You see this one, Bill?
Yes.
Okay, so what are the important components so that we can make room number 1 cold and room number 2 hot, really hot? What do you think?
I don't know what to call.
I don't, okay, you can try. What's that? What do you call that? Oh, Modtanoy has an answer. Okay, let us call Modtanoy. Bill. Okay, Modtanoy, tell us. That is correct, Modtanoy.
จริงเหรอ teacher
Read your answer. We have
condenser
Mhm.
compressor
and
evaporator.
all right, evaporator. Okay, that is correct. Okay, but in this case, this is just the same Modtanoy. Thank you so much. Okay, we have condenser, compressor, and evaporator. That is correct. Okay, so because in here we're talking about, okay, this one here is a transport medium. Okay, in this case, this transport medium is a piston. Okay, a piston with what's inside. Okay, what's inside is an evaporator actually. All right, an evaporator. For a refrigerator, this is a freon gas or ammonia. Okay, this is a transport medium. Okay, another one, Modtanoy said it's compressor. Okay, so in our example, a compressor is a piston, and then when you press the piston down, it makes the heat, it makes the environment hotter. Okay, that is the compressor. And the second one is actually a decompressor, but it's actually a condenser. Okay, condenser, according to Modtanoy. These are the same. Okay, the compressor or condenser. Okay, in here we absorb the heat, or it eventually makes the room cold because this transport medium absorbs the heat. All right. So these three are important. Okay. These three are important factors in making or pumping or transporting heat from room 1 to room number 2. Okay. Don't forget these three. Now, what's this? Okay, so first we're going to put a compressor from room 1 to room number 2, and then the compressor or the condenser, and then we connect that with this S tube, a lot of S tube, and then we compress. Okay, we compress the gas and make it hotter, right? Make it hotter. Okay, so what we are going to do is compress the gas in a compressor, okay, and make it hot. And eventually it is traveled up there in the decompressor, it becomes cooler, okay? And then down here on the other side becomes cold, okay? And then hot again here in the compressor, and then it is a process, okay? And then eventually if we're going to do this again and again, okay? Compressing the air and the gas and then decompressing to make it hot and cold, we can make one room or room number 2 hotter and room number 1 cold. Okay, so eventually we will have a hot room and a cold room. All right, what we actually did is we pump the heat from room number 1 and bring it to room number 2. All right, so as I was saying, we can actually pump the heat out of the first room and take it to another room, making room number 1 really cold and room number 2 really hot by just compressing and decompressing it. Okay, so in this case, we have here, this is the back of a refrigerator. Okay, this is the back of the refrigerator. And as you can see here, we have it is made up of a compressor and a decompressor, right? Or what do you call that? A condenser, okay? If you will look at here, we have number 1, 2, 3, and 4. And this one here on number 2 is a compressor, and number 3 is a condenser, or Modtanoy said that is, what's that? Decompressor, okay? So what happened is that refrigerator works by taking heat from the interior. Okay, so let's say one here is the inside of the refrigerator. So it works by taking the heat from the inside of the refrigerator and deposit it on the outside. Okay, so meaning we are going to pump the heat from the inside of the refrigerator outside, okay, and bring it outside of the refrigerator, okay, from one place inside to another place outside. Okay, so the compressor here raises the pressure and temperature of the refrigerant. Okay, the refrigerant is, what is that? That is the either a gas or a liquid that turns into a gas, right? Refrigerant. While the coils outside the refrigerator allows the hot refrigerant to dissipate, okay, to release the heat. Okay, so we have here number 1. If you're going to look at here, let me check. Number 1 here, it will absorb the heat from inside. It will pass through here from the compressor, okay? And then the compressor will pass through it here. And then we have here the refrigerant, okay? Refrigerant. And then it will pass through here. This number 3 is a decompressor or the condenser. Okay, so the condenser here will now dissipate the heat outside, and it will now be cool, okay, cold air, and it will be, we have here pass through number 4, expansion bulb. Okay, so in here it will evaporate on this phase. Okay, repeating this cycle, okay, repeating this cycle of over and over again will make the inside of the refrigerator cooler and the outer side hot, okay? But you cannot feel that inside in our room, right? Because it is dissipated into the environment. Okay, that is how a refrigerator works. Okay, it works by like this. Okay, there's a cold reservoir and then the hot reservoir. Okay, what happened is that it will pump the heat, okay, from the inside, okay, to the hot reservoir. But in order to do that, according to the second law of thermodynamic, work is needed. Okay, work is needed, and in the process, it produces heat. In the process of doing work, it produces heat. Right. So the process of pumping heat from one place to another produces more heat. Okay. Now there's a positive and negative, good news and bad news about that. Okay. So the good news is that the bad news actually is that, okay, when let's say if you're going to teacher, I want to make my room cold, so I just want to open the refrigerator to make my room cold. Okay, you cannot do that. Okay, because when you pump the heat, okay, from the inside, it will go outside. Okay, and eventually if you do that, it will make your room, it will make the environment or your room even hotter. Okay, so it doesn't uh, do the function of that. Okay, and the good news also is that we can do this by making devices like this one. We still have a few minutes. Okay, we can make devices like electric heater and a heat pump. Okay, now we can do this too. We have here on the right side a heat pump and an electric heater. Okay, so these devices can be used if you are living in places where you want to make your room hot or cold, like if you are in the US or in other cold places sometimes. Okay, so what is happening here is that for the electric heater and the heat pump, okay, we have here the units of electricity and the units of heat. For the electric heater, it consumes the units of electricity, okay, is +1, okay, meaning it consumes a +1 unit of electricity, and same with heat pump, okay, for a unit of electricity. But for the unit of heat, okay, the electric heater absorbs +1, but a heat pump, it becomes +3 in here. Okay, teacher, is it correct? This one here is obvious. It follows the law of conservation of energy, right? It should be balanced. But in here, +3, does it violate the law of thermodynamics? Okay, some way, it does not violate, because we are pumping, remember, we are pumping the heat from the cold room. Okay, cold room, so meaning we're taking the heat from the cold place, plus it develops heat by itself. Okay, because the engine becomes hot when it is doing work. Okay, so therefore the heat here is greater. Okay, the units of heat is greater than the unit of electricity in a heat pump. Okay, that is why it is important here. This one is a very important consideration when installing either an electric heater or a heat pump inside in places or in cold places. Okay, to take into consideration, whether you're going to install electric heater or a heat pump. Okay, all right, so this is how electric engine works. Okay, next is, let me see. All right, so it's finished, right? All right, so do you have a question, class? It's exactly 1:40. Do you have a question? Okay, I have here a quiz, but since it's a time already, I'd like to give you the quiz in our next lesson on Thursday. Okay, about the application of thermodynamics and heat engine. All right, everyone?
Teacher,
Yes.
can you send the PowerPoint in the live group?
Yes, please. Again, please.
Can you send the PowerPoint into the live group?
Yes, okay, I will. Okay, including the video.
Okay,
I
thank
have
you.
recorded the video. All right, thank you. Okay, that's all for today. It's time already. I'm going to give you the quiz, the evaluation next meeting. All right, thank you for today. Bye bye, everyone.
Thank you, teacher.
Thank you.
Thank you.
Thank you, teacher.
Thank you. You're welcome.
Thank you, teacher.
Thank you. You're welcome. See you tomorrow.